Now, in this lecture, we find out the area of the green shape. In the drawing, we have a circle. The radius of this circle equals to 2 units, r equals to 2. And we also have inside this circle peripheral angle ACB that is equal to 70 degrees in its size. And we have also the common external point P. From the common external point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle at point B. Our mission is to find out the area of this green shape. So, point O is the center of the circle. We join points O and B together by a straight line. Repeat again that point O is the center of the circle, point B is the point of the circle itself. Therefore, OB, line segment OB is the radius of this circle that is equal to 2 units. We can implement here all 1. Repeat quickly on all 1. According to all 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So, in the drawing we have a circle, and we have this tangent AB that is tangent to this circle here at point M. And we have the radius OM is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, rule 1. We can implement rule 1 in our drawing. Why? Because in our drawing, we have the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. And this angle equals to 90 degrees according this angle equals to 90 degrees according to rule 1. Likewise, we have the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 13, and according to rule 13, the central angle is twice as large as the peripheral angle subtended on the same arc. Okay, so repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have, this is the peripheral angle ACB that is equals to 30 degrees in its size, and it is subtended on this arc, arc AB. And they also have the central angle AOB, this central angle AOB is subtended on the same arc RKB. Therefore, according to this rule 13, the central angle AOB will be twice as large as the peripheral angle ACB. And because of the fact that the peripheral angle ACB equals to theta, therefore the central angle will be equal to 2 theta. Okay, so we can actually implement rule 13 in our drawing. Why? Because in our drawing we have the peripheral angle ACB that equals to 70 degrees in its size. This peripheral angle ACB is subtended on RKB. Repeat again. This peripheral angle ACB is subtended on this arc RKB. And we also have the central angle AOB. This is the central angle AOB. This is subtended on the same arc RKB. And therefore, according to rule 13, the size of this central angle must be twice as large of the size of this peripheral angle ACB that is subtended on the same arc RKB. And because of the fact that peripheral angle ACB is 70 degrees, therefore the central angle must be equal to 140 degrees. It is twice as large as the peripheral angle that is subtended on the same arc. Therefore, the size of the central angle AOB must be equal to 140 degrees. In the next step, we will join points P and O together by a straight line, those 2 points. By joining points P and O, we created here 2 right triangles, the right upper triangle, triangle AOP, and the right lower triangle, triangle POB. In the next step, we prove that those 2 right triangles can go into each other. Okay, so we prove that the right upper triangle, triangle AOP is congruent to the right lower triangle, triangle BOP. Okay. So why those 2 right triangles can go into each other? First of all, side AO of the right triangle AOP, of the right upper triangle, triangle AOP, is equal to side OB of the right lower triangle, triangle OBP. AO equals to OB, because both of those 2 sides are the radii of the circle, therefore they are equal to each other. Repeat again. Side AO equals to side OB, they are both the radii of the circle. Each side equals to 2 units in its size, or it is the radius of the circle that is equal to 2. In addition, we have side OP is the common side that belongs to both triangles, so we can write down that OP equals to itself. It's the common side that belongs to both triangles. Repeat again. OP equals to itself. It's the common side that belongs to both triangles. And finally, side PA of the right upper triangle, triangle POB, of the right upper triangle, triangle POA is equals to side PB of the right lower triangle, triangle POB, according to rule 2. PA equals to PB according to rule 2. I will remind you quickly what is rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So in the domain we have a circle and we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB, and according to this rule 2, they are equal to each other in their lengths. This is to say PA equals to PB. We can actually implement rule 2 in our drawing. Why? Because in our drawing, we have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. Again, PA equals to PB according to rule 2. So actually proved that all the three sides of the right upper triangle, triangle POA are correspondingly equal to all the three sides of the right lower triangle, triangle POB. Therefore, those two right triangles can go into each other according to side rule. So write it down. The right upper triangle, triangle AOP is congruent. This is the sign of congruent to the right lower triangle, triangle BOP according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore those two corresponding angles must be also equal to each other. So this is angle AOP in the right upper triangle AOP. And it is equal to this angle, this is actually angle BOP in the right lower triangle, triangle BOP. It again, I found out that angle AOP equals to angle BOP. So if we define one of those two angles as alpha, if we define this angle as alpha, then the other angle must be also equal to alpha because they are equal to each other. Okay. So alpha plus alpha, in total alpha plus alpha must be equal to 140 degrees, so you can see it from the drawing. Alpha plus alpha equals to 140 degrees. Okay. Alpha plus alpha equals to 140 degrees. So 2 alpha equals to 140 degrees. We divide this equation by 2. And finally we get that the missing angle alpha equals to 140 degrees over 2 is 70 degrees. So this is angle alpha that is equals to 70 degrees in its size. And this is also angle alpha that is equal to 70 degrees. In the next step, we will focus on the right upper triangle, triangle AOP. The right upper triangle, triangle AOP. What is the value of tangent 70 degrees? Tangent 70 degrees equals to AP over AO. repeat again. Tangent 70 degrees equals to AP over AO. AP is the missing side, so we will leave it as it is. So it is AP over AO. AO is the radius of this circle, is equal to 2. Therefore, we substitute AO by 2. In conclusion, found out that tangent 70 degrees equals to AP over 2. Tangent 70 degrees is equals to 2.75. So 2.75 equals to AP over 2. Here we multiply this equation by 2 and finally we get that the missing side AP, is equal to 2.75 times 2, that is 5.5. We found out that the length of side AP is 5.5 units. This side AP equals to 5.5 units in its length. I repeat again that our mission is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of this green shape equals to the area of the right upper triangle AOP plus the right lower triangle BOP so actually the sum of the areas of those two right triangles will give us the area of quadrilateral AOBP. So the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape, the area that we are looking for, that is the area of this green shape. So we have to subtract from the sum of the areas of those two right triangles the area of this sector AOB. Repeat again. After we found out that the area of the green shape in total it is equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrilateral AOBP, and when we subtract from the area of quadrilateral AOBP the area of sector AOB, we get exactly the area of the green shape. Okay. So, what is a sector? A sector is part of a circle or a portion of a circle. We have here a circle. The green shape AOB is a sector of the circle. It is part of this circle. The green sector AOB consists of two legs. The first leg is AO and the second leg is BO. Both legs are the radii of the circle. Therefore they are equal to each other. And it also consists arc AB, that is the arc between those two legs AO and BO. We can say it is the small arc AB, because we can actually say that this is also arc AB that you can see it also as an arc between A and B, between the radius AO and the radius OB. So we can say that the small arc between points A and B is the arc that consists, that the sector AOB consists of. Okay, so in conclusion, sector AOB consists of two legs that are the two radii of the circle, leg AO and leg BO, and the small arc between those two radii, this small arc, and this is angle theta, that is the angle between the legs of this sector AOB. So what is the area of this sector AOB? The area of sector AOB equals to the area of this circle that contains the sector, that is actually pi r square, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again, the area of sector AOB, that could be any sector, equals to the area of the circle that contains the sector that is pi r square, times the angle between the legs of the sector that is theta, over 360 degrees. Okay. So we found out that those two right triangles can go into each other, therefore they have also the same areas. Okay, the area of this right triangle equals to the area of this right triangle because they can go into each other. So we actually can substitute the area of the lower right triangle BOP by the area of the upper right triangle AOP because they are equal to each other. So we'll do it now, and we'll get that the area of the green shape in total will be equal to the area of the upper right triangle AOP and here we'll substitute the area of the lower right triangle BOP by the area of the upper right triangle AOP because they are equal to each other, minus the area of sector AOB. So the area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP minus the area of sector AOB. Here the rounded line above AOB is the sign for a sector. It means sector AOB. Okay, sector AOB, and the square brackets is the sign for the area. So in total, this expression means the area of sector AOB. So we find out the area of the right upper triangle AOP, we multiply it by 2, and it will be actually equal to the area of this quadrilateral AOBP. Okay. So what is the area of the upper right triangle, triangle AOP? The area of the right upper triangle AOP, actually the area of any triangle equals to the base of the triangle times the height to the base over 2. The height must create 90 degrees with the base. So if we take the base of this right upper triangle, triangle AOP is AO, the height will be AP. Why the height will be AP? Because of the fact that AP creates 90 degrees with the base AO. So the base of the right upper triangle AOP is AO, that is the radius of the circle, times the height to the base is AP, divided by 2. repeat again that the radius AO equals to 2, therefore let's substitute AO by 2 times AP. We already found out that the length of side AP is 5.5, so we substitute AP by 5.5 divided by 2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with 5.5. In conclusion, we found out that the area of the upper right triangle AOP equals to 5.5 square units. So I write it down. The area of the upper right triangle AOP is equals to 5.5 square units. So we have to multiply the area of the right upper triangle AOP, that is 5.5, by 2. 2 times 5.5 is 11. So actually found out that the area of this quadrilateral AOBP equals to 11 square units, because 2 times the area of this right triangle AOP equals to the area of this quadrilateral AOBP. Therefore, the area of quadrilateral AOBP equals to 11 square units, and we have to subtract from the area of this quadrilateral AOBP the area of this sector AOB. So it is 11 minus the area of sector AOB. What is the area of sector AOB? The area of this sector AOB equals to the area of this circle that contains the sector, that is actually pi r square, and r equals to 2, times the angle between the legs of this sector, that is actually 140 degrees, over 360 degrees. I repeat again, we actually found out that the area of this sector AOB, is equals to the area of the circle that contains the sector that is actually pi r square, times the angle between the legs of the sector, that is 140 degrees, over 360 degrees. So it is pi, and r is 2, therefore r square is 2 squared, that is 4. So in conclusion, we found out that the area of the circle that contains the sector AOB is 4 pi. So it is 4 pi times 140 degrees over 360 degrees. This expression, 4 pi times 140 degrees over 360 degrees, in total it is equals to 4.888 square units. Repeat again, we actually found out in conclusion that the area of sector AOB is equals to 4.888 square units. Okay. The area of the green shape is equal to the area of this quadrilateral AOBP, that is 11 square units, minus the area of this sector AOB that we just right now found out, that is 4.888 square units. 11 minus 4.888 is 6.111 square units. In conclusion, we found out that the area of the green shape is equal to 6.111 square units. repeat again. The area of this green shape equals to 6.111 square units. Okay, so in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So, in the drawing, we have a circle. We know that the radius of this circle r equals to 2 units in its length. Inside this circle, we have this peripheral angle ACB that is equal to 70 degrees in its side. In addition, we have in the drawing of the question the common external point P. From the common external point P, we have two tangents to this circle. Tangent PA, that is tangent to this circle here at point A, and tangent PB, that is tangent to this circle here at point B. Our mission is to find out the area of this green shape. So, in the first step, we join points O and B together by a straight line. O is the center of the circle, point B is the point on the circle itself. Therefore, line segment OB is the radius of this circle, that is equal to 2 units in its length, r equals to 2. So we can implement here rule 1. We have the radius OB, that is 1 to point B, that is the point of tendency of tangent PB with this circle. And according to rule 1, whenever you have a radius that is 1 to the point of tendency, then tangent PB will be perpendicular to the radius PO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees. Likewise, according to the same rule, rule 1, we have the radius OA, that is 1 to point A, that is the point of tendency of tangent PA with this circle. And whenever your radius that is 1 to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. Then I presented to you a new rule, and we implemented the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. Repeat again on rule 13. A central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing, we have a circle. Inside this circle, we have peripheral angle ACB, that is equal to theta degrees in its size. This peripheral angle ACB is subtended on this arc AB. In addition, we have here the central angle AOB. This central angle AOB is subtended on the same arc AB. Therefore, according to this rule 13, the size of the central angle AOB that is subtended on the same arc AB as the peripheral angle ACB will be twice as large as the peripheral angle ACB. And because of the fact that the peripheral angle ACB equals to theta, it means that the size of the central angle AOB must be equal to 2 theta. It is twice as large as the peripheral angle ACB. Okay? So, we can implement rule 13 in our drawing. Well, in our drawing, we have peripheral angle ACB. This is peripheral angle ACB. This is equal to 70 degrees in its size. We also have the central angle AOB and peripheral angle ACB that is equal to 70 degrees in its size is subtended on this arc AB. And we have also the center angle AB that is subtended on the same arc AB. Therefore, the center angle AB must be twice as large as the peripheral angle ACB. And because of the fact that the peripheral angle ACB equals to 70 degrees, it means the center angle must be twice as large as the peripheral angle. Therefore, the center angle must be equal to 140 degrees in its size. So, we probably found out that the center angle AOB, this center angle AOB equals to 140 degrees in its size. In the next step, we join points O and P together by a straight line. By joining points O and P, we created here two right triangles. The right upper triangle, triangle APO, and the right lower triangle, triangle BOP. So in the next step, we proved that those two right triangles, we actually proved that those two right triangles can go into each other. So why those two right triangles can go into each other? First of all, side AO of the right upper triangle APO is equals to side BO of the right lower triangle, triangle BPO. Why? Both those two sides are the radii of the circle, therefore they are equal to each other. AO equals to R, that is 2, and B also equals to R, that is 2. Repeat again. AO equals to BO equals to the radius of the circle, that is 2. Therefore they are equal to each other. In addition, we have side PO is a common side that belongs to both triangles, so we can write down that PO equals to itself is a common side that belongs to both triangles. Repeat again. OP, side OP equals to itself. It's a common side that belongs to both triangles. And finally, side PA of the right upper triangle APO equals to side PB of the right lower triangle, triangle BOP, according to rule 2. According to rule 2 states that the lengths of two tangents from a common extreme point to a circle are equal. That is to say, we have here the common extreme point, point 5, or the common extreme point, point 5, we have two tangents to the circle, tangent PA and tangent PB, and according to rule 2, they are equal to each other. That is to say, PA equals to PB. Repeat again. PA equals to PB according to rule 2. So we actually proved that all the three sides of this right upper triangle APO are correspondingly equal to all the three sides of the right upper triangle PBO. Therefore, those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding angles must be also equal to each other. Again, we found out that the two corresponding angles AOP and BOP they are equal to each other according to the rule that I mentioned. So if we define this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha in total, they must be equal to 140 degrees as you can see from the drawing. Alpha plus alpha equals to 140 degrees. Here, alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, that is equal to 140 degrees. We divided this equation by 2 and finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this is the missing angle alpha that is equals to 70 degrees in size, and this is also angle alpha that is equals to 70 degrees. Okay. In the next step, we focus on this right triangle APO. In this right triangle APO, tangent 70 degrees equals to AP over AO. Again, tangent 70 degrees equals to AP over AO. Repeat again. In the right triangle APO, tangent 70 degrees equals to AP over AO. AP is the missing side, so we leave it as it is. So it is AP over AO. AO is the radius of this circle, that is 2. So we substitute AO by 2. In component further, the tangent 70 degrees equals to AP over 2. Tangent 70 degrees is 2.75, that's equal to AP over 2. Here we multiply this equation by 2 and finally found out that AP, the missing side AP, equals to 2.75 times 2, that is 5.5. In conclusion, found out that the length of side AP is 5.5 units. Okay. Repeat again that our mission is to find out the area of this grand shape. What is the area of this grand shape? From the drawing it is very easy to see that the area of this grand shape equals to the area of the right upper triangle EPO plus the area of the right lower triangle BPO. So the sum of the areas of those two right triangles will give us the area of quadrilateral APBO, and after we subtract the area of sector AOB from quadrilateral, the area of quadrilateral AOBP, we get exactly the area of this grand shape. Repeat again, the area of the grand shape in total equals to the area of the upper right triangle APO plus the area of the right lower triangle BPO. The sum of the areas of those two right triangles will give us the area of quadrilateral APBO, and we'll subtract the area of sector AOB from the area of quadrilateral AOBP, we'll get exactly the area of the grand shape. Okay, but we only found out that those two right triangles can go into each other, therefore they also have the same areas. And therefore we can substitute the area of the right lower triangle BOP by the area of this upper right triangle APO. Okay. Here we substitute the area of this right lower triangle BOP by the area of the right upper triangle AOP, because they are equal to each other, they have the same areas. And finally found out that actually the area of the grand shape equals to the area of the right triangle APO plus the area of the same right triangle APO, because we substitute the area of the right triangle BOP by the area of triangle AOP. So it is the area of the right triangle AOP twice minus the area of sector AOB. Again, the area of triangle AOP plus the area of triangle AOP is 2 times the area of triangle AOP minus the area of sector AOB. So, what is the area of the right upper triangle AOP? The area of any triangle equals to the base of the triangle times the height to the base over 2. So, here, what is the area of this right triangle APO? We took the base as AO, and therefore the height to the base is AP, because they create 90 degrees with each other. So, the base is AO, and the height is AP. Repeat again. The base is AO, and the height is AP divided by 2. AO is 2, AP is 5.5 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and we left only with 5.5. And when we found out that the area of this upper right triangle APO equals to 5.5 square units. So we multiply the area of this right triangle APO by 2. In this way we get the area of this quadrilateral OBP. So 5.5 times 2 is 11. In conclusion, we found out that the area of the right, the area of quadrilateral AOBP, this quadrilateral AOBP equals to 11 square units. And we have to subtract from the area of this quadrilateral AOBP, the area of this sector AOB. Okay, so it is the area of quadrilateral AOBP, this is 11, minus the area of sector AOB. So what is the area of sector AOB? Okay, again, on the definition of sector, sector is part of a circle. The grand shape AOB is sector. It consists of the two radii of this circle and the small arc between those two radii, this is AB. And the angle between the legs of the sector is theta, and therefore the area of this sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of the sector, that is theta, over 360 degrees. Repeat again that the area of the sector in total AOB equals to pi r squared times theta over 360 degrees. So, what is the area of sector AOB? It is equals to the area of the circle that contains the sector that is pi r squared. If the area of this circle that contains sector AOB is pi r squared because the radius is r. And we have to multiply the area of the circle that contains the sector times the angle between the legs of this sector. The angle between the legs of this sector AOB is 140 degrees over 360 degrees. So it is 140 degrees over 360 degrees. R, the radius R of this circle is 2, therefore R squared is 2 squared, that is 4. So R squared is 4, so in total the area of the circle that contains the sector is 4 pi times the angle between the legs of the sector that is 140 degrees over 360 degrees. The value of this expression in total is 4.888 square units. In conclusion, found out the area of this sector AOB is equals to 4.888 square units. So the area of the green shape in total equals to the area of quadrilateral AOBP, that is 11 square units, minus the area of this sector AOB, that is 4.888 square units. And 11 minus 4.888 is 6.111. In conclusion, found out that the area of this green shape is equals to 6.111 square units. Okay, thank you very much.